The first part of what I'm going to do today is basically tell you how you arrive at the angular momentum commutation relations without reference to any specific quantum system. And the reason why I do that is basically this is how you would also figure out, say, commutation relations for Poincare generators and so on, essentially the same basic trick. And moreover, it's a very important physical application. And while you have already seen the angular momentum quantum relation, commutation relations in specific examples, you may not have seen the general treatment. And so one thing that often happens is while, for example, spin has the same kind of commutation relations as orbital angular momentum, that is often treated as something of a mystery. You are just sort of given that, okay, let's have three operators or three matrices which commute in this way, and we are going to call that spin. But once again, this is basically elementary stuff, something you could have also learned, in fact, should have also learned in quantum mechanics. So I'm going to skip over some of the steps, not too much. So I hope you will be able to follow the basic procedure here. So basically what you start with is the idea that rotations, say an element of SO3, this is a 3x3 rotation matrix, corresponds to a transformation U of R which acts on the Hilbert space of states which describe a quantum system. I'm keeping deliberately silent about what kind of quantum system we are dealing with. So I don't really know whether it's described by a single function, the wave function, or by a multiple component wave function. Could be any of those. I'm not really talking about that right now. Okay. So I have a specific quantum system in mind on which when you carry out a coordinate transformation, that is, you rotate your coordinate system, the description of a given state changes, and it changes so that psi gets acted upon by U of R times psi. Okay? And as we argued the other day, if R1, R2 equals R3, then you can argue that U R3, which is U of R1, R2, of course, has to be U R1 times U R2. This has to be taken with a small grain of salt, in the sense that we also talked about this thing last year, projective representations. That is, you could have an extra phase factor here, which could have depended on both R1 and R2, and also perhaps on the state phi. And you can argue that it doesn't. But still, the fact that you could have had a phase factor here is not ruled out by basic quantum mechanics, because quantum mechanics only talks about states up to a phase. But the same basic advantage that quantum mechanics, or basic redundancy in quantum mechanics, can be used to our advantage in this case, so that you can redefine the phases of your states, and you can always ensure that UR3 is exactly equal to UR1, UR2. Now, that you can always do this for rotations is one thing. There are certain other situations where a projective representation is essential. That is, you may have to have a phase. We are not going to go into that right now. For us, we are just going to look at a non-projective representation, which is the simple case that UR3 is UR1, UR2. In other words, this map U essentially is a homomorphism from the group SO3 onto the group of linear transformations, or at least a subgroup of the group of linear transformations which act on your Hilbert space. Is this clear so far? Any questions about this? Okay, if not, let's move on to this very basic and important point here, which is rotations can be built up. In small steps, right? Even when we are talking about big rotations, You can think of a very small rotation about an axis, then another very small rotation, another very small rotation, maybe along the same axis, and they all add up together and you end up with a big rotation. So small rotations are an important building block. Now, a null rotation, no rotation at all. What is the matrix representing that? When I say matrix, I mean R. Which R represents that?
The identity.
The identity matrix, right? There's of course a 3 by 3 identity. I'm not going to say 3 by 3 explicitly, but it should be understood. So small rotation can be thought of as basically identity plus a small extra piece. This matrix omega, this is a 3 by 3 matrix, of course, which has to be added to the identity. And when I say small, I mean each of the non-zero, each of the components here in omega are tiny. Tiny compared to the typical, okay, you cannot say it's tiny compared to the corresponding element in identity. After all, identity has ones along the diagonal and zeros on off diagonal position. But typically the scale of the identity is the number 1, and each of the elements in omega are either 0 or they are very small compared to 1 in size. Okay, this is what a small rotation would mean to us. Now, an immediate consequence of RTR equals identity, and this of course means that there are higher order correction terms possible. This is only to first order in omega. Will immediately tell you that omega and omega transpose must add up to 0. That is, omega is antisymmetric. Okay, omega ij and mine is negative omega j. Okay, so that means that the number of parameters which are there in the matrix omega, and that this should not come as a surprise, is the same as the number of parameters of a 3 by 3 antisymmetric matrix, which happens to be 3. This should not be a surprise because even an arbitrary tiny rotation would usually be described by 3 parameters. All SO3 matrices are described by 3 parameters. And we talked about the parameter space before, but right now we are looking not at the complicated part of the parameter space, what happens near a pi rotation. We are looking at very tiny rotation. Okay, so deep inside the SO3 ball, somewhere near the center, we always have matrices which behave like this: identity at the center itself, and identity plus omega, where omega is antisymmetric. Okay, so what about the corresponding U of R? Well, especially what about U of this? So when I say I plus omega, I mean tiny rotation. So what is the corresponding operator for a tiny rotation? Well, it's easy to see that for no rotation at all, it should be the identity operator in that space. So what do you have here? You have these parameters omega 1, 2, omega 1, 3, omega 2, 3, all these parameters, they actually tell you what the rotation is, right? So what you expect for this U operator to be like is it would deviate from the identity, but to first order an identity, it will basically be omega ij times jij, and I'm assuming some over I and j here. Okay, right? Omega 1 3 to j1 2 plus omega 1 3 to j1 3 and terms like this. Okay. Now, two things. One is we throw in a half here. The half simply because, first of all, what is important to realize is omega 1 2 j1 2 is there. Similarly, omega 2 1 j2 1 is also there, right? You have terms like omega 1 2 j1 2 in this sum. You also have omega 2 1 j2 1. So basically, you actually have omega 1 2 into j1 2 minus j2 1. Okay. So it's only the antisymmetric part of j1 2 of jij's which actually contribute. If jij's were symmetric in the indices or had a symmetric part in the indices I and j, then that would not contribute in this sum at all. That's the signature of the fact that you have omega, which is antisymmetric in the interchange of I and j. Okay. And because of this, what we do is we assume that Jij and Jji are negatives of each other. By doing this, we are only keeping the relevant portion. The symmetric part, a part which is symmetric in I and j would be completely irrelevant as far as the sum is concerned. We're just dropping that. We are assuming that our j's are defined in this way. So J12 and J21 are negatives of each other, right? And if I do that, then of course what happens is this sum actually counts each piece twice, right? So that's why you have a half. Any questions about this?
So what exactly is Jij? Is it like the omega term
Jij's
of?
are, of course, look, U is an operator, right?
Yes.
So whatever is sitting here has to be operators. This
Yes.
is the change of U from the identity operator with the parameters omega 1 to omega 1, 3, and so on. So these are, of course, omega 1 to omega 1, 3 are just numbers, right? These are elements of the omega matrix, capital omega matrix. So these are numbers. So this has to be operators, right? These are operators which act on our state space. Okay.
So we can think of it as something of similar to U of omega.
Well, U of omega is an operator. So are Jij's, but Jij's are basically the way, basically tell you that when you move away from the null rotation, how do U operators deviate from the identity? In other words, basically Jij are the derivatives of U with respect to omega, right?
Okay. So this is basically
This is Taylor
Taylor.
expansion. This is
Oh,
Taylor
okay.
series, first
Oh,
order, nothing
okay.
else.
Okay.
Okay. And of course, that means there are higher order terms, omega squared terms, which we are ignoring here. We are not writing them. Is that okay?
Yes, sir.
But there's something else that you do. This is basically physics, which is you throw in an extra factor of I over H cross. Okay. Two reasons. Why do you throw in the I? Because throwing in the I will ensure that since U's are unitary, if you throw in the I, that will ensure that the J's will be Hermitian. Now, if this were a purely mathematical thing, we would not care too much about Hermitian operators as opposed to anti-Hermitian operators. But in physics, of course, Hermitian operators play a very important physical role, which is why I would want these operators, which are generators of rotation for that space, right? They essentially tell you what happens when you do a tiny rotation. But remember what happens to the state vectors when you do a tiny rotation. But also remember that big rotations can be built out of small rotations. So if you know what happens for small rotations, you essentially know everything. So J's essentially tell you how rotations act on vectors. Okay. And in classical mechanics, if you remember your canonical transformations, then you also have a concept of generators. And there the generators of infinitesimal rotations happen to be angular momentum. That's a purely classical mechanical thing. From there, we draw a parallel and say whatever generates rotations in quantum mechanics is what I'm going to call angular momentum. Does this make sense? In fact, the textbook that you must have used in quantum mechanics, which textbook did you use, by the way, for quantum mechanics? Or which textbooks?
We used R. Shankar's one for advanced quantum mechanics.
Okay. You didn't look at Sakurai, for example?
Yes, sir. We
Yes.
followed that as well.
Yeah, but Sakurai, if you read the beginning of Sakurai, Sakurai actually identifies various operators which act on quantum states with their classical counterparts by essentially saying that they do the same thing to the states that those classical operators, classical dynamical variables do as generators of infinitesimal translations. In fact, this part is, you could have just taken this right out of Sakurai, except with the notation perhaps. Okay? the identification of GIJs as angular momentum operators, and there are three of them, right? Although this looks like there are nine, but you should realize that because of Gij equals minus JJI, all the JII is a zero, and if you know three off diagonal pieces, when I say off diagonal, I mean I not equal to J pieces, you know the other part. So there are only three independent such J operators, which is exactly very nice because that's exactly what we have for angular momentum. Clear? And because these J's generate rotations, and angular momentum in classical mechanics generates rotations through infinitesimal canonical transformations, we identify these operators as angular momentum. Okay. Now, the precise form which this operator will take will depend on the particular system you're talking about. Okay, clear?
Yes, sir.
But there are operators which act on your silver space. Now, what we want to do is figure out the commutation relations which these JIJs will obey, and we will do that using a very simple thing. The basic idea is U of R prime inverse R prime has to be, according to our basic demand, that use furniture representation equals this, right? Or maybe I will switch the R and R prime, doesn't matter, this is fine. Okay, right? You agree?
Right.
So what I will do next is choose, okay, that's why I said I will switch the R and R prime, write these outer ones as R, the one which is actually inducing the similar transformation, and say the inner rotation here is an infinitesimal one. So say I plus omega. Okay. So this is a matrix corresponding to the a similar thing to an infinitesimal rotation. Okay. And that will be UR inverse U of I plus omega. UR shouldn't come as a surprise, right? But notice what this is. This is, look at the matrix inside. R inverse I plus omega R is really R inverse R, that's of course the identity, plus R inverse omega R. Okay? Now this is infinitesimal if omega is. You all agree to that?
Yes, sir.
So what we have is, we have gone from one infinitesimal rotation, which was given by this I plus omega matrix, to another one. But that will of course be UR inverse identity plus I by 2H cross omega I j j I j sum over I and j. And please don't confuse this I, which is square root of minus 1. I don't want to invent a entirely new notation for that. But this is square root of minus 1. That's not an index. You are. You agree?
Yes.
So let's take a look at what this tells you. This tells you that, okay, this one is also an infinitesimal rotation. So this will be identity plus I by 2H cross R inverse omega R klth element jkl. And on this side, we have identity, which is UR inverse identity UR, plus I by 2H cross omega I
So how is
j.
it the same J on LHS? Like, shouldn't it be a different J?
Should it be? When I did
Because
this rotation, when I wrote this down, should it be different J's really?
because you said J is the partial derivative with respect to omega, and here is the
Right,
partial.
at omega equal to 0, right?
Okay, okay, okay,
Taylor series, right? It's not,
okay.
it doesn't depend on the value of omega. If it did, then this would not be the first order thing.
Yes, yes.
Taylor series derivatives are taken at where you are expanding about. So omega, in fact, the whole beauty of this is I can change the omega ij's, and this formula still uses the same g ij's, right? Otherwise, this would be a completely useless formula.
Yes, sir.
Okay, so it's the same j, not a different set. That is, I just using j, kl simply. So this is u r inverse j I j u r, right? Because omega ij's are just numbers. and use the linear operators, you just jump through them. Okay. So I will now execute my first jump and tell you that this, if you read it off carefully, will tell you this. I'm not going to explain where this comes from. This is something you should be able to figure out very easily. Okay. With just one thing that you have to bear in mind, these R's are orthogonal matrices. That's important. So R inverse is the same as R transpose. Okay. So that's homework, how to go from here to here. But once you have got this, can anyone tell me what does this tell you about the JKLs? This tells you how the JIJs transform when you rotate your coordinate system. And on the right hand side, you have the result. This, of course, sum over both K and L. I'm not just not writing that. But this fact that JIJs, when you transform them, when you rotate your coordinate system, the JIJs change to a linear combination of the J's with two factors of R in front. What does it tell you about the J's? What kind of an object has this transformation rule under rotations?
Vector.
Vectors. Vectors don't. Vectors transform with one factor of R. Come on. You have two factors of R. What kind of an object has two factors?
Rank 2 tensor.
Could you be a bit louder? I couldn't hear you.
Rank 2 tensor.
Rank 2 tensor. What kind? Contravariant, covariant, what kind? And when I put them in a bracket, it means all of the JIJs together, of course. Is there? Rank 2, what kind of tensor? Contra or co? Any idea? Actually, the answer is it does not matter. Does not matter meaning, as far as rotations are concerned, there is no distinction between contravariant or covariant vectors. In fact, as far as any orthogonal transformation is concerned, contravariant and covariant tensors behave exactly the same way, which is why you manage to go through life for quite a long distance until you hit GR, where you talked about transformations other than orthogonal ones. When you really seriously started talking about them, you could go through life until that point without ever knowing that there is something like a contravariant or a covariant object. Under rotations, there is no distinction. Both transform the same way, which means they're both just tensors. But this is, of course, antisymmetric, because we have already postulated that. But didn't we actually know that that angular momentum is a vector? Did we know that? Here I'm saying there is an antisymmetric rank 2 tensor. Is there something wrong with this? Any ideas? Okay, I will let you worry about that. Let's move on to the next step anyway. The next step essentially is, now that we have got this, I will basically use this, and here I will take are to be infinitesimal. Note that I started with taking the rotation in the middle of this similar transformation as infinitesimal and arrived at this. But this is true for all capital R, which means it's true for the case where R is infinitesimal. So what does this give me? U R inverse. Now, since R is infinitesimal now, remember U R is identity plus I by H cross 2H cross. Right? I will just use that. I will put this UR on both sides. And of course, that means Rij or Ik, the kind of thing that happens, comes here, is delta Ik plus omega Ik, where omega Ik are infinitesimal patterns. Yeah? Now, if I put this, what will UR inverse be? Can anybody help me out with that? Of course, there are higher order terms. I'm just writing the first order. What will UR inverse be? You of course know what UR will be. UR is just identity plus I by 2H cross omega KL JKL. I'm not dropping the higher order terms anyway. What about UR on this side? UR inverse on this side. What will that be? Come on, if this is UR, what's the inverse?
Just switch the indices.
Just switch
R-
which indices? Both of them. These are dummy
No.
indices, nothing to switch. UR has no indices, right? Well, actually,
1 minus iota by 2H cross.
yeah, right. Basically, what you are doing is using the fact that this is a unitary transformation. And so its inverse is the same as its adjoint. And remember that JKLs were rendered Hermitian by putting in the I. In fact, if you multiply this with this, you can easily show that the up to first order the J terms will cancel and you will get the identity. That's what you have on this side. On the other side, you have delta RIK, which is delta IK plus omega IK. RJL, which is delta JL plus omega JL. JKL. Okay, further homework. You should be able to use this. Now, by the way, when you open this out, identity Jij, identity will give you Jij. But on this side, delta Ik, delta JL, JKL, that will also give you Jij. That should be obvious. So Jij will cancel it. Terms like this times this times this, I will not bother about. Why?
The order of omega square.
They're order omega square, so you can't take them into account because you have already dropped order omega square term here, comes here. But the first order term, of course, you can handle, and you should be able to notice that if you take the first order terms, you are going to end up with what actually? This times this, that's one term, and this times this, that other term. Right? So what will I get? What kind of a very familiar thing will you get from here?
A commutator or anti-commutator.
Come on. If you multiply this in this order and in this order and take both these terms, what do you get? Yes? Shouldn't that be obvious? This is an operator, this is another operator. You multiply them. Another term is one in which you take this operator and this operator multiply them.
A commutator or an anti-commutator?
Well, in this case, what will you get? You will actually get the commutator because
Commutator, yeah.
the first
So
term comes with the minus sign, the other term comes with the plus sign. Okay. So on the left-hand side, you will get the commutator multiplied by omega KL. That is, of course, contracted with omega KL. On the other side, you will get Jij, which has already cancelling out with this, plus first order terms. So homework. From this, you should be able to read off the commutator. I by H cross commutator with Jij, JKL. This is iota, of course. That's a good thing about calling that iota. Although I'm not sure why anybody calls that iota. It was always meant to be the letter I for imaginary. Of course, making it Greek sounds more sophisticated, but still. This commutator can be worked out. Actually, this commutator will have 4 terms. The first of one, I find this very easy to remember this way. There are many ways of writing this, by the way. I find it very easy to write it this way, that delta IL JJK, that is, you take the outer indices, I and L, take the inner ones. Put one of them on delta, the other one on JK, on capital J. Okay, that comes with a plus sign. In fact, swap the two, that also comes with a plus sign. And the other option, which is take the first index here, second index, second index, that comes with minus sign. Delta IK, JJL. This should be pretty easy to figure out, except that you have to bear in mind one very important thing, which is this. If you get omega ij, aij equals omega ij, bij, does this imply aij is the same as bij? Remember, omega is arbitrary. This works for all rotations. So just hold on. I need to take a call. That's all. Yeah, tell me.
Only the symmetric part would be the same.
No. Actually, it's just the opposite. Only the antisymmetric part will be the same. That's because omega ij is antisymmetric in inj. Any symmetric part that you have, say, if S were symmetric,
Okay, it'll go to 0. So
go to 0. Because omega, if you get to interchange I and j, here nothing will change, here will become a minus sign, but interchanging dummy indices, of course, never change the value. So symmetric parts won't contribute. Antisymmetric parts contribute. Okay? Right? And as a result, you can only, when you write down these two sides, because the omegas are antisymmetric in their indices, only the antisymmetric part on both sides will match. Antisymmetric meaning you have omega KL times this, so antisymmetric in K and L. This part is already antisymmetric in K and L because if you change K and L, JKL becomes JLK, you get a minus sign. And the commutator, of course, if one term gets a minus sign, the whole thing gets a minus sign. The other side, which you will get directly from here, is actually not antisymmetric in KNL to begin with. So you have to do an anti-symmetrization. That's the only slightly tricky part. Okay. But once you have done that, you end up with this, which is the angular momentum commutation relation. Two things. One, it looks pretty nice. Okay, it looks horrible if you ask me. But frankly, it's really not very difficult to remember. You just remember one term. Take the two outer, two inner, put with a plus sign. The rest of the terms, even if you have forgotten completely, you can figure out from the fact that this whole thing has to be antisymmetric if we have to swap I and j. So note, from here I've swapped I and j and I got this minus sign. It would have been antisymmetric. So would have to pick up, look at the next left hand side. Where to interchange ij, you get a minus sign. So on the right hand side also, so you must have that. Similarly, interchange k and l, you must pick up a minus sign on the left, so must pick up a minus sign on the right. These two are actually related to each other with interchange by changing k and l. And if you take both interchange I and j and interchange k and l, of course you will get two minuses which makes a plus, and that's this term. So just remember one term, the others you can write down just from the antisymmetry. It's not that difficult. Okay, clear? But the other question that should immediately come to you is this really the angular momentum commutation relation? Doesn't it look horribly more complicated than the ones we already knew? Actually, these are the angular momentum commutation relations, with one small catch. They have been written in a different notation. And for this, you have to realize that any antisymmetric matrix, the ones we wrote down, well, what did we write down? These have to be zeros. Omega 1, 2, omega 1, 3, omega 2, 3. And these are, of course, negatives of that. But I can also use, since there are only three parameters, I can also write it this way. I can write P zeros, of course, I can't do much about that. Omega 1, 2, I will just call omega 3. Omega 1, 3, I will call minus omega 2, and omega 2, 3, omega 1. The minus sign here is basically because 1, 2, 3, 1, 3, 2, 2, 3, 1. You should notice that two of them are in cyclic order. They have the plus signs. The other one has a minus sign. Otherwise, what I've done is I have essentially written down omega I is a single index omegas in case of the omega ij case. And basically what I've done is sum over j and k and a half. The half again is really because when you write this down, you get contributions both from omega 1, 2 times epsilon 3, 1, 2 and epsilon 3, 2, 1, omega 2, 1. So double thing. Okay. And vice versa. Omega ij, that epsilon ijk, omega j. No double counting here, no half. Check using the property of the epsilon symbol that these are consistent. Okay. And then this sum, omega 1, 2, j 1, 2, which is actually this. Or I could perhaps write omega 3, 1, j 3, 1 if I. Okay. Is it okay? This was a sum, right? The first order correction. You actually had a 2 here, but I have not put down the 2 because I have just taken into account that omega 2, 1, j 2, 1 will give you the same term. Okay, and similarly. This is the same. I can rewrite this as omega 1 J1 plus omega 2 J2 plus omega 3 J3. That is I by H plus omega vector dot J vector. By just essentially saying that I'm going to call J1 2, which is multiplied by omega 1 2. Omega 1 2, note this is omega 3, right? So J1 2 is J3. J31 is multiplied by omega 31, which is omega 2. So this is actually J2. And this is J1. This is just a re-nomenclature using this notation. So I'm just like omegas, I can also rewrite the J's. The Ji's are half epsilon ijk jjks. And very similarly, the Jij's are epsilon ijk jk. So there are only three independent ones. I've just put in three of them. Clear? After this, you should be able to either use the properties of the epsilon symbol, it's pretty easy to do, or just write it down case by case and show that the commutation relations we have obtained are exactly these. Okay? Is that clear?
Yes.
So basically, it's just a different way of writing the thing. And the two-index notation is a bit cumbersome for our simple angular momentum words. So we perhaps would prefer this simpler one-index notation. But there's a bigger reason for this. Remember, I we wrote as epsilon ijk jjk. I wrote it. So the half of epsilon ijk jjk. Okay. So how would rotations change the GIs? Well, it will be essentially this. We already know this, that UR inverse JJK UR essentially is what happens to these capital J components under rotational coordinates, and we had already figured out that it transforms like a second rank tensor. Antisymmetric second rank tensor, but second rank tensor. Okay, so this is the way in which GIs transform. But there is one hugely important result which you should be able to figure out yourself. Can anybody tell me what this is? Epsilon ijk ri p r j l r k m. Some of us, can anybody tell me what quantity is this? Forget the fact that these are rotation matrices. For any 3x3 matrix, can you tell me what this stands for? Quickly. Quickly, we don't have much time, so but come on. This is something which you have known from your higher secondary days. Maybe not in this notation. But what are you doing? You're multiplying Ri three elements from a 3x3 matrix.
It's like a cross product.
No, this is much more elegant. Where is the cross product coming from here? Cross product is there somewhere.
The determinant.
This is the determinant of R. But actually, this is not the German alpha. This is epsilon PLM times German alpha. If PLM were in the order 1, 2, 3, which this means you're taking the one element for the first column, then another for the second column, another for the third column. But this is pretty straightforward. This is just think of how you defined the determinant long ago. You would see this is what you were really doing. Okay. Now, using this result, you should be able to convince yourselves that this quantity, half epsilon I jk jk, which is basically J1 elements with J12 minus J21, J13 minus J32, and so on, basically is a vector. That is, an antisymmetric second rank tensor is equivalent to a vector. That happens only in 3 dimensions. And you mentioned the cross product, and you were right. That is precisely why a cross product is a vector only in 3 dimensions. When you form a cross product, what you do ax by minus ay bx, this kind of stuff, right? These are the components you put in the cross product. Now, since you're multiplying component by component 2 vectors, you basically are doing what is called an outer product of 2 vectors, which is a rank 2 tensor. But you're also antisymmetrizing it. And a rank 2 antisymmetric tensor in 3 dimensions, and only in 3 dimensions, is essentially the same, has the same transformation rule as a vector does. Which is why basically cross products exist only in 3D, and which is also why the angular momentum operator, which is really an antisymmetric second rank tensor, can also be thought of as a vector, or to be more precise, a pseudo vector. These are all known things, right? That angular momentum is a pseudo vector and so on. Yes? Then the cross product exists only in 3 dimensions. And that is why R cross P, even when you thought of L as R cross P, you essentially, we are creating a pseudo vector which transforms like vectors under rotations. And where you could explicitly calculate the commutation relations using the elementary QI-PJ commutation relations, the canonical commutation relations, and show that for that Li, Lj was the I epsilon ijk Lk. Is that okay? Any part of this is unfamiliar? If no, can I move on to the next part? Or is this okay?
It's okay, but just this part that anticipated rank 2 tensor can be thought of as a vector 3D. This was unfamiliar.
This was not known.
Yes, at least to me.
Okay, good. So I've learned something at least. But this happens only for rotations in 3D, and happens only in 3D, which is why the cross product is not such a great thing to use. But also, since we live in a 3D world, it has been very useful for us. Okay. Now, let's quickly move on to some more apps. This is what concrete SO3 group generators, or SU2 also has the same commutation relation for generators, basically because close to the identity that behave the same way. Okay. So let me now just go back a bit to the abstract, but not too much. Now, from this, you should also know that J1 plus minus IJ2. These are familiar things, right? These are J plus minus operators, the raising and lowering operators. So J3 and J plus minus. You also know the commutation relations they obey, right? Don't.
Yes.
What is J plus J minus commutator? right? And J3 is commuted with J plus minuses. Is this okay? Well-known stuff, right?
Yes, yes, yes.
Now we are going to use a slight variant on this because that's going to make it more useful easy for us to do some calculations. We are going to talk of an app. So these were J1, J2, J3, which generates our SU2. Actually, that's really wrong. IJ1, IJ2, IJ3. These are basis vectors for SU2. Right? Is it okay? Or small SO3, both the same thing. When I say IJ1, IJ2, IJ3, note that this change from the identity. This is this extra piece. These are basically like tangent vectors to the manifold of transformations. Right? You are moving away from the identity and you are looking for tiny changes. So J1 to J13, it's actually IJ1 to IJ13, IJ23. These are actually being linearly combined with real parameters. Omegas are all real. To give you the tangent space. Of course, here we are looking only at only infinitesimally close to the identity, but omega I guess could be big, and you big that would give you the whole tangent plane, right? So IJ1, IJ2, IJ3 are the Lie algebra basis vectors for SU2. Okay. Seen as a real Lie algebra. This is important. Okay. The change I talked about is a J plus, J minus, and J3. I will just use J plus, J minus, and I will use something called J0. I will just say 2J3 is J2. This is slightly unfamiliar, but it's easy to relate one to the other. So J0, J plus, J minus. They form basis vectors. This is, of course, a change, transformation. Sorry, 2J3 is J0. I've just linearly combined J1, J2, and J3, right? I've arrived here. So this is basically, you started with IJ1, IJ2, IJ3, which are basis vectors for SU2, which is SU2 is a real Lie algebra generated by IJ1, IJ2, IJ3. J0, J plus, J minus. Yes. Any idea which real Lie algebra does these two keys generate? Do they generate the same real Lie algebra? These generate SU2. What about these? Yes. What do they generate? Quickly. Same thing? We'll just change the basis, right? Well, actually, they don't. Can you see why? They don't generate the same real Lie algebra. And that should be very, very easy to see why. For example, is J plus even a member of the real Lie algebra generated by this? Can we form J plus by combining these elements with real numbers?
No,
No.
we can't.
So these two, although this looks like a change of basis, they do not generate the same real Lie algebra. They're not even parts of the same. Even IJ3 and J0, they're not in the same real algebra, right? You can't go from IJ3 to 2J3 by combining that with real numbers. Yeah. J plus does have an J2 in it, but it also the J1, which you can't get from IJ1 with real numbers only. Okay. So this is something you have to bear in mind. These two algebras are distinct as real Lie algebras. So although very, very, very often, in the most classical, in the most quantum mechanics textbooks will tell you that this is just a change of basis and these are also generators for SU2, they are not. Okay? They can help you learn stuff about generators of SU2 simply because you can get back the generators of SU2. J1, J2, J3, or rather IJ1, IJ2, IJ3 can be recovered from J0, J plus, J minus. And we use them often interchangeably, but seen as generators of real Lie algebra, they generate entirely different Lie algebras. This one generates all 2 by 2. Well, basically SU2, when exponentiated, this gives you the 2 by 2 unitary special matrices. And IJ1, IJ2, IJ3, when you combine them together, what you get are 2 by 2 traceless Hermitian matrices. Okay? Here, when you exponentiate a traceless Hermitian matrix with an I in front, of course, actually IJ1, IJ2, IJ3 gives you traceless anti-Hermitian matrix, to be more precise, into Y. And therefore, when you exponentiate them, you get exactly unitary, unit determinant matrices. J0, J plus, J minus, on the other hand, gives you traceless real matrices. And when you exponentiate them, you get unit determinantal real 2 by 2 matrices, which is why J0, J plus, J minus generates SL2R, and this generates SU2. Okay, this will be, I will give you a homework which should make this explicit in terms of matrix, 2 by 2 matrices. You can explicitly calculate and see that this is what happens. However, one thing is important. Very often we have already talked about complexification of Lie algebras, right? Which is basically you essentially combine them with complex numbers and treat them as a complex vector space. Now, it should be very easy to see. They both form in fact, if you thought of these as elements of a complex vector space, then it's easy to see that this is a genuine basis transformation. Okay? And that complex vector space happens to be SL2C. That of all unit determinantal 2 by 2 complex matrices. Okay? Well, that's the capital SL2C, that's a group. The algebra is set of all traceless 2 by 2 complex matrices. So strictly speaking, when you are working with J0, J plus, J minus, or IJ1, IJ2, IJ3, or J1, J2, J3, and allow complex coefficients, then you are not really talking about the Lie algebra for SE2 or SO3. You are actually talking about the Lie algebra for an entirely different Lie algebra, the SL2C. But since results from one can be obtained from another, we very often confuse or we ignore the difference. And we keep on saying we are using SU2. But in actual practice, most of the time what you're using is SL2C, which is often shortened to SL2. Okay, this distinction becomes clear. Now, these are different things at least. That the real D algebra spanned by this and the real D algebra spanned by these are different things. And whereas the complex D algebra spanned by them are the same, is that much clear? Whether they're called, what they're called may be a different issue, but is it much clear?
Yes, sir.
And the fact that these are generators of SU2 is something we have already seen, right? We explicitly started with rotations, which are homomorphic to SU2. This goes to the origin, they behave the same way. So this one was sort of obvious. Strictly speaking, is IJ1, IJ2, IJ3 which generate rotations, not J1, J2, J3. At least thought of as a real algebra. Okay. We deliberately stick in the I in our derivation in a formulae so that we don't have to talk about anti-Hermitian operators. But these are really the basic vectors of SU2, not J1, J2, J3 to be very precise. And J0, J plus, J minus that they generate a different real algebra should be obvious. And of course, they are very deeply connected to each other. And we are going to exploit that connection. I'm not going to exploit this connection, we are not going to exploit the connection very much in this class because we have already done an entire course on angular momentum in quantum mechanics, where you have used J0, J plus, J minus to tell you things about states. Right? What kind of eigenstates J1, J or J3 can have and so on. Maybe you didn't use J0, you used J3, but it's the same thing. I will not explore this very much, but I will need those results. So I will, next day, what I will do is I will give you a very quick alternate derivation of the results in angular momentum theory in quantum mechanics. That is about the states which we used to call J, M. But let me just ask you one thing. You did study all this, right? Jm and what J plus minus does to them, what J0 does to them. Although maybe you use J3 here. Can anybody tell me what this is going to be? J0 acute JM? Come on.
M times the state.
Actually twice M times the state.
Okay, 2.
Because J0 is J. And that actually has the advantage that here the eigenvalues are all integers, rather than possibly half-odd integers as well. And J plus minus essentially increase or decrease some function, do this, right? But when you derive this whole thing, you use the fact, for example, that J1, J2, J3 are Hermitian operators. So J minus is actually adjoint of J plus. All of these results you really use. And use the fact that there exists a J0, or J square, which commutes with all of them and so on. Okay. Now we are going to try to avoid, this one is still true no matter whether you're dealing with real algebra and so on. But we will try to avoid using the fact that J1, J2, J3 are Hermitian. We'll see that if you insist on finite dimensional representations of the SU2 algebra, you are going to get essentially the same kind of structure without having to explicitly demand that J1, J2, J3 are Hermitian. Now in physics, whenever we use them, most often J1, J2, J3 are Hermitian. So this looks like an unnecessary restriction. However, the basic structure that you use here can be used in many other places other than quantum mechanics as well. So it's good to know that you can actually get the same kind of results without assuming Hermitianity. And as long as you demand that representations are finite dimensional, you are going to end up with very similar results. So you want to show that quickly, but on Wednesday, we want to move on to basic SU2 theory quickly and then go on to SU3. But for that, I need to know one thing. Isospin is something all of you are familiar with. Isotopic spin.
No, sir.
Then read up before Wednesday. Take any elementary particle physics book. This doesn't, you don't really need an elementary particle course for this. Isospin is very basic physics. So, and anyway, there is a standard thing from which lots of questions come in exams like NET. So you should know what isospin is, at least at a very basic level. So take up any, in fact, most quantum mechanics books have this. If not, take up a simple elementary particle physics book, like say Griffiths. Read up about basic isospin. You don't have to read up much. You just need to know how you use the SU2 algebra, also in particle physics. Because once you know that, we can go on from there and talk about what we are going to do next is basically we are going to try to invent SU3. This is slightly different from the way it's done in most textbooks. And definitely different from the way we have been proceeding in this course. We have essentially been proceeding with general Lie algebras. But now, since you have not done the nitty-gritties of these special cases, I think it will be a good idea to see how, for example, Gell-Mann, when he looked at the, okay, we are going to pretend that we are like Gell-Mann, and we are going to try to sort of make sense of the things that we see in the particle physics world by introducing a new kind of symmetry. And what kind of course, new kind of symmetry will require new kind of Lie algebra and therefore new kind of commutation relations. Question is, can we deduce, or at least can we deduce the kind of commutation relations we need, or at least can we deduce the simplest version that will do the job for us? So this is different from doing abstract Lie algebra theory where you know that there is an SU3 group and therefore you should have an SU3 Lie algebra from that. SU3 is just 3 by 3 special easily matrices. They obviously form a group. They form a Lie group which can easily show is 8-dimensional. And so there should be 8 generators in the corresponding Lie algebra and so on. But we are not going to do that. We are going to pretend like we are just seeing all this for the first time. We know SU2, that is, we know angular momentum. And we should know that SU2 algebra can also be used in particle physics to essentially say that things like protons and neutrons, which are very, very similar if you leave out electromagnetic effects, are basically two states of the same superparticle, the nucleon. And uses the fact that that's an approximate symmetry as long as you don't take into account electromagnetic effects, to understand why the proton and neutron say have very similar masses, or why do pi plus pi 0 pi minus or k plus k minus, why do they have similar masses, or why do they really behave so similarly except when electromagnetism is involved. So that's what we start with. Then observation tells us that if you are not that finicky, protons and neutrons are really very close in mass. The 3 pions are almost identical in masses. But if you're not very finicky and don't want to be very, very accurate, you can actually see that there are bigger multiplets of particles which can observe. More particles with essentially same kind of properties, but different particles. And they essentially have very close masses. So what Gell-Mann did was to cook up another approximate symmetry from which you could explain this. And this, of course, led to the famous quark model. So we will essentially study the basics of the quark model on Wednesday and Friday. Not at great depth, but what exactly is involved here. And instead of taking a shortcut, which will say that SU3 gives you that structure, which is what most textbooks do, we'll try to see how you could get the structure by using a bigger Lie algebra than just SU2, and what kind of computation relations that must have. So I don't know whether Gelman actually did this when he actually set out, because Gelman, of course, was pretty well-read mathematically. That would be an understatement. So it's very likely that he already knew the SU3 multiplex. And so he could recognize that what he was seeing in the particles of his world were basically what SU3 would have given him anyway. That's a possibility. But the other possibility is he didn't know SU3 beforehand, which is possible because group theory was not really a great staple for physicists in those days. But he knew that as an isotopic spin, he also saw bigger multiplex arising than what isotopic spin could explain. So he tried to hook up the symmetry himself. So we will pretend that that's what happened, and we are going to do that over Wednesday and Friday. If I have time, I will also show how that relates to the general theory of Lie algebras, because whatever we are going to do essentially will be reflected in the general theory of Lie algebras. But since I think your classes end on Friday, right? Is that true?
Yes.
Or
Yes.
Yes, sir.
okay, so officially that will be the end of the course, but I will try to record another video later and talk about the general theory and tie it up with whatever this SU2 to SU3 process, whatever we discovered there, a generalization of that will play out in the theory of general semi-simple Lie algebra. So we are going to talk about that in a later video, but that will of course not be in the exam. Okay, so any questions? Okay, if not, let's call it a day today.